Hi. We're continuing with chapter 3. So we did section 3.1 in the last video. We're not covering section 3.2. We're going to skip it. The next section is 3.3 about zeros of polynomial functions. So I'm going to start by typing the fundamental theorem of algebra. This is not in the book. And the fundamental theorem of algebra says that if a function f is a polynomial function of degree n, where n is greater than 0, that is, you have at least a linear function, or if you have a non-constant polynomial, then f has at least 1 0, which can be real or complex. So what do zeros look like? Let's see. Okay, so let's say we have a polynomial function, f of x. It's x squared plus 3x minus 4. We can write this polynomial in factor form. This factor as x plus 4 and x minus 1. So this polynomial has 2 zeros, because f of -4 is 0, and f of 1 is 0. Okay, so -4 and 4, -4 and 1 are zeros of f. Number 2. The polynomial, consider the polynomial. I'm going to use a different letter. I'm going to call it g. X squared minus 6x plus 9. In factor form, this polynomial is going to be x minus 3 times x minus 3. Or if you want, you can write this as x minus 3 squared. So that's the polynomial in factor form. And you can see that g of 3, 0 g of 3, 0, and 3 is a 0 of multiplicity 2. You can also say that it's a double 0 or a repeated 0. But it's 0 of multiplicity 2, but because it appears twice. And number 3, we are going to bring back complex numbers. H of x is x cubed plus 4x. We can write this in factor form. We can first factor x. This factor as x times x squared plus 4. And x squared plus 4, we're going to factor it with complex numbers. That's going to be x times x minus 2i times x plus 2i. So h has 3 zeros. 1 real, and the other 2 are complex. The zeros are 0, the opposite of 2i, and 2i. In the book, this section starts with the factor theorem. On page 327, the factor theorem says that for any polynomial function, f of x, x minus k is a factor of the polynomial if and only if f of k is equal to 0. Like in the examples we did. F of negative 4 is 0, so x plus 4 is a factor. F of 1 is 0, so x minus 1 is a factor. Or g of 3 is 0, and x minus 3 is a factor, and so on. Okay, so the fundamental theorem of algebra has two consequences that I'm going to copy. This was, by the way, on page 330. Okay, but let me, well, let's indicate the page. That's to 327. And the fundamental theorem of algebra has two important consequences. The first one is on page 330. Okay, so I'm copying that. Actually, the fundamental theorem of algebra is on page 330. So one consequence is the number of zeros. A polynomial function defined by a polynomial of degree n has at most n distinct zeros, at most. It may have less than that. It may have some repeated zeros or some zeros of multiplicity greater than 1. And the other consequence is the complex zeros. That complex zeros come in conjugate pairs. Okay, so the first one, the number of zeros theorem, that's on page 330. And the conjugate zeros theorem is in page 332. So if f of x define a polynomial function, having only real coefficients, and if a plus bi is a zero of f, then a minus bi is also a zero of f. So the one I did, the example I mentioned, 2i is a 0, so minus 2i is also a 0. Okay, so we have important information. We're going to do some exercises on page 337. I'm going to copy the directions. We're going to find all the zeros and their multiplicities. Okay, I'm trying to copy that. This is on page 337. We're going to start with number 50. And let's, okay, let's adjust this sizes and everything. Okay, so number 50, we're going to find the zeros and the multiplicities of this polynomial function, of the polynomial function f of x. F of x is 5x squared times x squared minus 16 times x plus 5. So this is not in completely factor form. We can still factor x squared minus 16. So let's write this in factor form. That's 5x squared. And x squared minus 16, we can factor it as x minus 4x plus 4. times x plus 5. Okay, so this has 4 zeros. You know, you can write x as x minus 0. So this has the following zeros. 0 is a 0 of multiplicity 2. Actually, I'm going to write them in order. So I'm going to write them in increasing order. I'm going to start with negative 5, negative 4, 0, and 4. But 0 is a 0 of multiplicity 2. And if the 0 has multiplicity 1, we're not going to write that. If a 0 appears once, we're not going to say anything, just when the multiplicity is 2 or greater. In number 52, we have another polynomial function. We have the same question. We're going to find all their zeros and their multiplicities. Okay, so we have something to the third power. Let's rewrite this a little bit different. This expression raised to the third power can be factored as, well, for 2x squared, we have 2x and x. And then we want the combinations outside plus inside to be -7. So we have 3 and 1, and they're both negative. And x minus 2 minus square root of 5, we can rewrite this as x minus 2 plus square root of 5. Okay, so in factor form, this polynomial is going to be 2x minus 1 cubed times x minus 3 cubed times x minus 2 plus square root of 5. So that polynomial has 3 zeros. Trying to write this 5. And the zeros are going to be what? Are going to be, well, you know that 2x minus 1 equals 0 implies that x is 1/2. Okay, so the zeros are 1/2, 3, and 2 plus square root of 5. Where 1/2 and 3 have multiplicity 3. So 1/2 has multiplicity 3. And 3 has also multiplicity 3. Okay, so that was one type of example, identify the zeros and the multiplicities. The next type of examples, we are going to write a polynomial function with the given conditions. We're going to find a polynomial function that's still on the same page, 337. We're going to find a polynomial function f of x of third degree with real coefficients that satisfy the given conditions. On number 54, we have a description. That's a polynomial of third degree. That is, if it has third degree, it's going to have 3 zeros that can be real or complex. Well, they're going to be real. So that's third degree. And we know the 3 zeros. And we have another condition that f of 2 is equal to 3. Now we're going to start by writing the polynomial in factor form, but the final answer must be in general form. If you keep it in factor form, my MATLAB is not going to accept it. So initially, I know that f of x is going to be some leading coefficient a times. The zeros are 1, -1, and 0. So that's going to be x minus 1, x plus 1, and x minus 0, which is simply x. Okay, so f of x is a times, and then we have x, and x minus 1 times x plus 1 is going to be x squared minus 1. So we can use f of 2 equals 3 to find a. Well, actually, we can go a step further because this is a times. So that's ax, x squared. So that's going to be ax cubed. And ax minus a times x times -1 is going to be minus ax. So we can do that to find a. Knowing that a times 2 cubed minus a times 2 is equal to 3. But 2 times 2 times 2 is 8, so that's 8a minus 2a equals 3, and 6a is equal to 3. And a is 3/6 or 1/2. Okay, so that's going to be our polynomial function. So don't keep it in factor form because my MATLAB is not going to accept the answer. The polynomial function of third degree with those conditions are 1/2 x cubed minus 1/2 x. And number 58. I'll copy the description. We're going to find a polynomial function having a 0 of 2 and a 0 of 4 having multiplicity 2, where f of 1 is -18. So initially, I know that f has a 0 of 2, so that's going to be a times x minus 2. And if 4 is a 0, x minus 4 is a factor. Multiplicity 2, that's going to be x minus 4 squared. That's what I know so far. So what I'm going to do next is use the fact that f of 1 is -18. So f of 1 equals -18. This implies that a times 1 minus 2 times 1 minus 4 squared is -18. So that's -1 times -3 squared. But -3 squared is 9. 9 times -1 is -9. Divide both sides by 2, and a is equal to 2. Okay, so far I know that f of x, I found the value of a. So f of x, it's 2 times x minus 2 times x minus 4 squared. And we already found the polynomial. This answer is correct, but it's in factor form. And my MATLAB will not accept it until you write this in general form. So that's not much of a problem. We can just distribute. X minus 4 squared is x squared minus 8x plus 16. Or if you want, you can just go ahead and multiply 2x minus 4. You can distribute the 2 and write 2x minus 4. And then let's distribute 2x times x squared minus 8x plus 16. That's going to be 2x times x squared. That's going to be 2x cubed. 2x times negative, the opposite of 8x. That's minus 16x squared. And 2x times 16 is 32x. And then distribute the 4, that's minus 4x squared plus 32x minus 64. Okay, and finally combine like terms. And we're going to find the formula for the polynomial. That's 2x cubed minus 16x squared minus 4x squared plus 32x plus 32x minus 64. So that's the type of answer that my MATLAB is going to accept. And I have two more examples. This is, as you see, this wasn't a very long section in the last two examples. So this will involve complex zeros. We are going to find a polynomial function of least degree, having only real coefficients and zeros as given. As some multiplicity 1, unless otherwise stated. So that's what we mean with, that's what they mean with least degree. Don't try to increase the multiplicity unless they tell you that the multiplicity is not 1. So number 54. And it doesn't say anything about the leading coefficient, so we're going to keep things simple and let the leading coefficient be 1. So we know that complex zeros appear in conjugate pairs. Since complex zeros appear in conjugate pairs, I and 2 minus I are also zeros. And it doesn't say anything about the multiplicity, so we assume that the multiplicity is 1. I have some information. I know that f of x, let's keep it as simple as possible. We're going to assume that the leading coefficient is 1. So that's going to be x times x plus I times x minus I times x minus 2 plus I times x minus 2 minus I. So x plus I times x minus I. That's going to be x times, and then we have x squared minus I squared. That will become x squared plus, that's going to become x squared plus 1. Then I'm going to do the following. X plus 2 minus I, I'm going to rewrite this as x minus 2 minus I times x minus 2 plus I. So that's x times x squared plus 1. And then we have x squared, or not x squared, x minus 2 squared minus I squared. Okay, so we have made some progress. I will distribute this x. X times x squared is x cubed plus x. And then x minus 2 squared is x squared minus 4x plus 4. And then minus I squared, that's going to be plus 1. And I need to, yeah, that's, I'm multiplying the whole thing. And let's combine the 4 and the 1. This is x to the third plus x times x squared minus 4x plus 5. So last step, we're going to distribute the x cubed and the x and combine like terms. Okay, so distribute x cubed. That's going to be x cubed times x squared. And then minus 4x, so that's going to be minus 4x to the fourth. And plus 5x cubed. And then x times x squared. Minus 4x squared. Plus 5x. So final answer, the polynomial with those conditions is going to be x to the fifth minus 4x to the fourth plus 5x cubed minus 3x squared plus 5x. So this is our final answer. And the last example is number 72. That's going to be the last one. Same question, we're going to write a polynomial of least degree, having only real coefficients, and zeros as given. And unless stated otherwise, the zeros have multiplicity 1. Okay, so 2 plus square root of 3 and 2 minus square root of 3 are zeros, and 2 plus 3i is a 0. This means that 2 minus 3i is also a 0 because complex zeros appear in conjugate pairs. So initially we have that f of x. We're going to start by writing in factor form. That's x minus 2 minus square root of 3 times x minus 2 minus negative square root of 3, that's plus square root of 3, times x minus 2 minus 3i times x minus 2 plus 3i. Okay, so we're going to do some things. We're going to group the x minus 2. This is x minus 2 minus square root of 3 and x minus 2 plus square root of 3. Then x minus 2 minus 3i and x minus 2 plus 3i. That way we have products of sum and differences. So x minus 2 minus square root of 3 times x minus 2 plus square root of 3 is going to be x minus 2 squared minus square root of 3 squared. And x minus 2 minus 3i times x minus 2 plus 3i is going to be x minus 2 squared minus 3i squared. We're moving forward. X minus 2 squared is going to be x squared minus 4x plus 4 minus square root of 3 squared is going to be 3. X minus 2 squared, that's again x squared minus 4x plus 4. And 3i squared is going to be 9i squared. So that's 9i squared. But we know that I squared is negative 1. So that will become plus 9. This is x squared minus 4x plus 1 times x squared minus 4x plus 4 minus 9 times -1. That will become plus 9. And this is x squared minus 4x plus 1 times x squared minus 4x plus 9 plus 4 is 13. Okay. We're going to distribute. Let's distribute the terms of the first polynomial. So x squared times the second polynomial is going to be x to the fourth minus 4x cubed plus 13x squared. The opposite of 4x times the second polynomial is minus 4x cubed plus 16x squared minus 52, that's, yeah, minus 52x. And 1 times the second polynomial is x squared minus 4x plus 13. Okay, so final answer. Combine like terms. X to the fourth. Then minus 4x squared minus 4x squared. 13x squared plus 16x squared plus x squared. It's 30x squared. 30x squared, and that one is a third. That one is a 3. And then 52x minus 4x is minus 56x. And the constant term. So that's going to be the final answer. And this covers section 3.3. Thank you for listening.